In this lesson, we are going to discuss the Diffie-Hellman algorithm. It's very similar to RSA, but there is a subtle difference. In here, we can make sure that the key is same on the both sides, but you can't transfer any data. Throughout this lesson, you may be asking why we need Diffie-Hellman. Why can't we simply use RSA? We'll address that in the end. But RSA always can transfer data and kind of superset of Diffie-Hellman. But Diffie-Hellman is slightly older algorithm and still used for key exchange. It's a key exchange only algorithm, while RSA can be used for key exchange as well as data exchange. Another good thing with Diffie-Hellman is that from the learning perspective, we can give an analogy. A good analogy is possible for Diffie-Hellman using the paint, which we will discuss. But at the end, we will get into the maths as well to get into the real stuff. And we will finish the chapter with some discussion around it, including quantum cryptography, attacks, and things like that, which breaks the prime number factorization problem. Without further introduction, let's get into it. So the first thing we would like to discuss here is a key exchange algorithm. We had a quick look into the puzzle before where we are exchanging some common information using box and locks. It's like a brother algorithm in terms of key exchange with the RSA. In fact, Diffie-Hellman is invented before RSA, and there is a difference as well. So Diffie-Hellman, the name is based on the scientist who invented it, Diffie-Hellman. You can check in Wikipedia. In fact, we will look at Wikipedia for examples. So the idea is fairly straightforward. It is based on one single equation. Suppose we have two numbers, S1 and S2. S1 is one secret and S2 is another secret. Let me name it SA and SB because we have Alice and Bob. 1 and 2 can be confusing. SA and SB. So you will feel familiarity with something you have done so far, which is the RSA, because it is also using the modular arithmetic or modular arithmetic. I'm afraid to pronounce the word module or module. Module is the correct pronunciation, but a lot of my Indian students doesn't understand when I say module. So it is modular arithmetic or modular arithmetic, depends on how you pronounce it. So both these numbers has the following relationship, provided we have two more numbers, G and N. G and N is public, just like in the case of public key RSA. So G and N is known to everyone. Now we can write this following equation right here. G raised to SA mod N, G raised to SA mod N, the whole raised to SB mod N equal to G raised to SB mod N, the whole raised to SA mod N. So this is the central equation to Diffie-Hellman. So we'll get into the details of it a little bit here, but this is what we are going to use as the key exchange algorithm in certain cases. And we will discuss how it is being used in the key exchange. But this is the equation which underpins the idea. And SA and SB, these numbers are secret numbers to both parties. They are not going to share this one particular bit to the world. But in the end, they will have a shared secret. So this value right here is a shared secret. This is the shared secret. If you calculate this value, it is a shared secret. And it is exactly same for both parties. But both parties are not transferring these numbers to each other. No one knows other than themselves. Exact same technique we used in the case of that puzzle thingy we discussed before. This is known to everyone. N and G is known to everyone. It is publicly available information, N and G, but SA and SB is not known to anyone. Also, this calculated number right here, the total number, this number is also known to anyone, only to two parties, both A and B. So what are the things Eve knows? Alice and Bob knows the calculated number as well as one secret. What Eve knows? Eve knows just N, G, and this bit as well. So let me draw that in the color, different color. So I'll use blue. So Eve is blue. Eve is the attacker, man in the middle. So E knows G, so the stuff here, and N, the stuff here, and this bit as well. So this bit is known to E, as well as this bit right here. This is also known to E. These things are public. But E doesn't know, I'll draw it in another color. E doesn't know this bit. This is not known to E. Same as this, which is exactly same. So that is the summary of the algorithm. So let's get into a little more details. First, let's get a feel of it. So there is a traditional way of explaining Diffie-Hellman using colors. So let's try that. It's a very intuitive way of understanding this algorithm. I was kind of discussing the math. Normally people start with this color thingy, but you have already gone through the RSA. You have already gone through a bigger pain. So I started with the math so that you will get a concrete feeling before I get into the analogy. But the analogy will make it feel better. Feel free to watch all these videos again and again until you feel comfortable, along with so many other things out in the internet. So we are going to get into the color thing right here. So we are going to have Alice and Bob. So this is Bob, Alice, and Bob. Now both has different color palettes. So let's draw that. So Alice has a red color palette. So this is red, and she has a red paint in it. That red is a secret. So this is Alice's secret. So she's not going to share this with anyone, including Bob. What is the ultimate goal of Alice and Bob? Have a common information, common number, if you will. So that's the ultimate goal. So Alice has the red. Let's draw the secret color of Bob, which is blue. So this is blue. So this is the secret color of Bob. So Bob has blue color as secret. So this is the private boundary of Alice and Bob. It's the private boundary. So this is the public area. This is where Eve is there. Eve is available here. She's ready to hack anything and everything. Very smart person. Eve is available in the public. Now, the idea is to have a common color between Alice and Bob without Eve having it. That's the whole idea. Another goal of the exercise is Alice and Bob doesn't want to expose their color as well to anyone, including Bob. So that is another agenda we are having. Same with Bob. Bob doesn't want to expose his color. So we have seen this in RSA. We can do this in RSA very efficiently. Use the public key and encrypt and send it to Bob using Bob's public key. So like I mentioned, Diffie-Hellman was invented before RSA. So this was one of the way to exchange keys before RSA. With RSA, definitely we can do what we are going to do, but RSA had patent and a lot of other things around it. Even today, Diffie-Hellman is used in SSL, but it is not a requirement. It is an optional algorithm used for key exchange. We'll discuss that when we discuss the SSL. Now, coming back to our story, there is a known color to everyone. That color is, say, green. This is known to everyone, a common color. So this is green. That is even known to Eve. So this is known to Eve. That's why this arrow is there. Same color is available everywhere. Green is available everywhere. It's not secret. Green. It's a common color available to everyone. Even Bob has that green. Same green. No change. Exactly same green. Again, Bob is also sharing that with Eve and the whole public world. Now the idea is what Alice is going to do is she is going to mix this green and this red. Let's do that. So this is the green. She take the green one in a bottle like this, a palette, and she will put some green inside it. She will pour some green inside it. So this is the public green. Now what she will do, she will put some red, her secret red, into that. This is how she is doing the mixing. So she is doing the mixing here. You know what is the problem with this mixing? This cannot be unmixed or taken out. No one can figure out or taken out this red from this mixed bottle, right? This is a mix of both green and red. What color we get if we mix green and red? I have no idea. It should be blue, something like that. Anyway, we are mixing green and red. The only thing we need to understand here is we cannot unmix this. We cannot take the red out of this liquid. That's the assumption. Now what we are going to do, we are going to give this to Mr. Bob through the public network. Miss Eve also has access to this. Eve can see this particular liquid, but she is not able to figure out anything because she cannot understand what color mix is this. She knows that one color is green, but she doesn't know what is the other color. She cannot differentiate this particular thing from this liquid. That's the idea. Now what Bob does, Bob is also going to do the same thing. He is gonna mix his blue with green. So let's see that, blue and green. He's also taking his green into a bottle like this. The public green into a palette like this. Now what he's going to do, he's going to mix the blue here like this. What we get when we mix blue and green, again, I don't know. When you mix colors using paint, it is not exactly same rule as the RGB, but it's just a detail which doesn't matter here. So Bob has mixed his paints, green and blue, and again, there is no way to differentiate or take out the blue from this mixed liquid. No one can find out. What he's going to do, he's going to send that to Alice. The mixed liquid is being sent to Alice. Alice got that mixed liquid. So let's draw that here, this whole thing. So we have the green bottle here with green paint, and here also we have that. Now this is the blue bottle sent from Bob. Bob is sending blue. It's basically the same thing. And here it's the red. So red is available here. So this is from Alice and this is from Bob. Now what is Bob and Alice going to do next? They are going to mix their own colors, their own secret color to what Bob sent. So this is sent from Bob. This is Bob's and this is Alice. What they're going to do? They're going to mix their own color to what the other party sent. So let's do that. So in the case of Alice, Alice is gonna mix all this three, red, blue, and green. Again, here also, Bob is going to mix his own blue color into what Alice has sent. So red, blue, and green. As you can see here, whatever this particular mixture right here is exactly same as both parties. So this is equal to Alice and Bob. And Eve cannot make this particular mixture right here because she doesn't have access to these colors. So right now we are in a position that we have not transferred this information, but we have a common information between Alice and Bob. That's the idea. Both Alice and Bob has mixture of red, blue, and green. So what is the color we get when we mix red, blue, and green? It is definitely not white because, as I said, mixing colors are different from constructive mixing of colors. Check that. If you mix red, blue, and green, you will not get white. It doesn't matter. We don't know. Some color, probably something like black. Whatever it is same for both Alice and Bob. That's the idea. So this is the crux of Diffie-Hellman key exchange. The mathematics we already discussed. What we can do is, to make us feel slightly better, we can go through an example of the calculation we have seen before using Copilot, like we always do. Again, Diffie-Hellman is not really required. It's an optional algorithm. It'll come in certificates pretty often because it's used at the moment. So we will discuss an optimization, shortly discuss an optimization called elliptic curve cryptography. Just an optimization. We are not going to get into the mathematical details of elliptic curve that needs its own training, probably multiple training like this. So we will summarize what elliptic curve in this session itself before we go into the SSL/TLS part of the training. So right now, let's see an example for all this color thing we have discussed, all the mathematics we have seen in the beginning of the training. So I'm going to type here Diffie-Hellman key exchange with small numbers. I typed the spelling wrong. I hope it gets right. Yeah, it does. All good. So we have all the calculation right here. Let's have a look. So we have P and Q. In fact, we have P and G. P equal to 23 and G equal to 5. That is the number it is taken. And the secrets of both Alice and Bob is A equal to 6 and B equal to 15. This is a number they are not going to share with anyone other than themselves. Not to Bob, not to Eve, not to the public, not to anyone else. These numbers are going to be secret. If this number is compromised, everything else is compromised. So these are secret. And these are going to be public, these numbers are going to be public. And A is calculated, which is G raised to A, G raised to secret of Alice, mod P, which is 5 raised to 6, mod 23. We have seen similar calculations before. 5 raised to 6 mod 23, which is this particular number, mod 23, pretty big number. Mod 23 is 8. And this 8 is visible to everyone. This 8 is visible to everyone. Bob, Eve, public, Alice, everyone. This is visible to everyone. This is a public information, right? Same Bob does, very symmetric. Diffie-Hellman is very symmetric. Exactly same thing done by both parties. G raised to B. B is the secret of Bob. G raised to B. Mod P, which is 5 raised to 15. Mod 23, huge number right here. Mod 23 is 19. Again, this 19 is transmitted to the public network. No security whatsoever. It is visible to everyone. Eve, Bob, Alice, everyone. So this is the information Bob is giving to the network, to the public. So Alice gets this and Bob gets this, Eve gets this, everyone gets this. Although it is sent to Bob, it is sent to everyone. This is transmitted to everyone. It's like a broadcast if you want to think about it. Now, this is the important part. What we are going to do with capital A and capital B, public information. So the calculation is exactly symmetric like I discussed in the beginning of the training. B raised to A mod P equal to 2. So this is the calculation Alice is going to perform. B raised to A mod P. This is the calculation. Look at this equation. B raised to A mod P. And we get the result 2. 19 raised to 16 mod 23 mod this number mod 23. The result we get 2. And this is a calculation Bob is going to perform. A raised to B mod P, which is 8 raised to 15 mod 23, which is this huge number mod 23. Again, we are getting 2. And 2 is the secret between Alice and Bob. Eve can't see this 2. That's the crux of everything. Eve cannot see this 2 because Eve cannot do this calculation because Eve doesn't have A. Similarly, Bob has B, so he is able to perform this calculation. Eve doesn't have it. So that's how at the end Alice has 2, Bob has 2 as well, because these two equations are equal. There is a equal to sign like I put in the beginning of the training. So feel free to look at it if you want. I can save this as well, but you can simply search for this or look at the Wikipedia page as well. So this is the summary of the calculation. If you want to have a look, pause the video and have a look. So this is the Wikipedia page for Diffie-Hellman. You can read more about it. So this is kind of what we discussed. Let's have a look. So this is the nice little image here. So we have Alice and Bob. Alice has secret 4 and Bob has secret B. Same thing we saw. P equal to 23 and G equal to 5. By the way, P is a large prime number. Also, these things are prime numbers. And we test this calculation. G raised to A mod 23 equal to 4. This is not a very good example. They should have given a different example. In this case, the secret is equal to the data you are transmitting to the whole world, which is not a good example. It can confuse you. Just go with the example I have shown or create your own example. The problem with this example is this 4 is not equal to this 4. This 4 is a different calculation which is not known to or not related to this 4. Anyway, we got 4 there. We are giving to Bob and Bob is doing similar things and both of them ending up 18 as the common secret. So that is the Diffie-Hellman key exchange. This is the paint thingy we discussed. So we have common colors. Common paint is there, which is yellow in this case, yellow. And we have red and some kind of blue, which is the secret. Is it blue or green? I don't know. But they are secret colors and they are mixing. So when we mix these two colors, we get this color. That looks around correct to me. And when we mix these two colors, we get something like this. And we are transmitting those colors across each other. And they are mixing their own colors. And finally, they are obtaining the common color. Yeah, these colors looks much more realistic than the image which I have drawn. I was expecting the common color is some darker shade like this. That's what happens when you mix colors in paint. It's not like when you mix red, blue, and green, you get white. It doesn't work that way. All right, so that is the color thingy in the Wikipedia. So this is the mathematics around it. Feel free to read more about it. Some of the details we have not discussed. It is explaining how those two equations are equal. It is not very trivial because of the presence of mod. There's a lot of things to learn in modular arithmetic. These are the different attacks available towards Diffie-Hellman. So whenever we read about anything in security, it's a general thing I'm telling you, anything in security, whether it's RSA, whether it's SHA-256, whether it's Diffie-Hellman, doesn't matter. Anything and everything about security, make sure that you read about the attacks as well. I'll be focusing a little less on the attacks part of the training because the training gets very complicated and very big and very rigorous if we start explaining all the attacks. I'll see if I can cover some attacks in the end of the training, but otherwise I'll be paying less attention to attacks. Attacks needs a certain amount of rigor to it, otherwise even explaining attacks doesn't make any sense. Normally student sleeps when I explain all these things, probably even you are sleeping now. But my kind advice is go through the attacks, try to read about it. That will help you understand the algorithm better, as well as you will get to know the weakness of the algorithm. Now a little bit about something called elliptic curves. So we are not going into the details of elliptic curves, but you will see this in almost all the cipher suits every now and then. So I want to make sure that you have an idea about it. So g raised to x mod y equal to z. So we use this kind of equation almost everywhere. So let me write this c in a proper way. G raised to x mod y. Y is normally a very large prime number, and g and x, mostly x is the secret at some point, and g is also the public exponent more than often, especially in the case of something like Diffie-Hellman we have seen. Now the crux of this thing is that given z, which is almost always public, it is literally impossible to calculate x. That's the whole point of this particular equation. So you have y, you have g, you have z. The task is to calculate x. Draw that in a different color. So x is a secret. You have g, you have y, and you have z. So you know the equation as well. Now solve for x. There is an inherent difficulty for doing this. This is the backbone of a lot of these things we have seen so far. Even RSA for that matter. Diffie-Hellman, RSA, all these public things where you give things publicly. So these things are public. There is a public element to it. So these things are public. These white things are public. Now what elliptic curves does is optimize this part of the calculation using certain curves and points in the curves. If you want, you can think of it like a compression of keys. For example, if these numbers are very small, like the one we have seen in the example from Copilot, you can easily deduce it. You can easily find it out. Say for example, if g equal to 5, y equal to 7, and a z equal to some 18 or something, you can try and find this thing out. Because of that reason, we have to use pretty big numbers for these values right here. Very big numbers like 4k, 2k, 1k, all pretty big numbers with thousands of digits. And the calculation gets complicated. It's not easy to calculate with those numbers. That is where the elliptic curve comes into the picture. So elliptic curve reduces a number, the amount of keys or the size of the key with the same amount of security. That's what elliptic curve does. The elliptic curve keys are very short compared to almost 10 times shorter than non-elliptic curves. Again, elliptic curve is an optional thing, but it compresses the key size by reducing this equation to a much more simpler mathematics. The goal of elliptic curve cryptography is pretty much the same thing. You have couple of public things, the white ones here, and making it difficult to find X with a reduced number of or reduced amount of key size. That's the idea behind elliptic curves. So modern days we use ECDH. ECDH. I'm sure someday you will see ECDH somewhere. So whenever you see ECDH in some kind of cipher suit, ECDH means elliptic curve Diffie-Hellman. So it's a Diffie-Hellman, but which is optimized with elliptic curve type of key and different equations like this, which satisfies the same purpose. So this is the Wikipedia for elliptic curve cryptography. I don't recommend or I don't ask you to read any of these things because it's not really needed for the purpose of this particular training, or unless you are getting into the details of cryptography, we don't need to get into it because it needs a certain level of mathematical background. Probably all I ask you to read is probably this much, which is what we kind of discussed so far. And if you want to know more about it, we need to understand details of this kind of things. Elliptic curve discrete logarithm problem, which is similar to the factorization problem we discussed in the beginning, but it's not that trivial. So these are the different algorithms which are optimized using elliptic curve. Almost all has elliptic curve in front. Diffie-Hellman, the digital signature algorithm. So we have seen the digital signature algorithm, which is optimized with elliptic curve to reduce the key size. So you will see ECDH and ECDSA pretty often, which is used in SSL these days. And these are some of the attacks on this particular technique. Almost always these public key algorithms, even RSA, Diffie-Hellman, even elliptic curve for that matter, is prone to Shor's algorithm. So Shor's algorithm is an integer factorization algorithm using quantum cryptography or quantum computing. It's very theoretical as of now at the time of this presentation, but it has the potential to factorize large integers theoretically. So there are new quantum safe algorithms are there. Shor's algorithm is an algorithm which factorizes integers, finding the prime factors of an integer. That's what it does for large numbers in polynomial time. But it uses quantum techniques, quantum mechanical techniques. Nothing much bothers us at the moment in time. Just putting it out there because when you read through these things, you will see this word quantum all the time. So that's why I'm putting that word out there. So to conclude, I hope it was not too complicated. At least it is not as complicated as RSA. Still, it has a lot of common ground between RSA and Diffie-Hellman, especially the equations and the way it generates the keys. And we have seen how quantum cryptography or post-quantum cryptography is slightly different. And all these algorithms has to be cryptographically safe from the quantum perspective. A lot of organizations save the data, like I mentioned. Saves the data such that when a quantum break comes in future, they can decrypt and look into the data. So saving to decrypt in the future. But in practice, most of the cases, all the algorithms which we use are not cryptographically safe from the quantum perspective. That's all for this lesson, and see you in the next.